Assalamu alaikum, dear students. We continue our work. It's part 3 of lesson 3.2 photoelectric emission. Okay, so we continue solving questions. We were solving before question number 3, but we didn't finish it. We didn't finish from it. So here was the aim, if you remember, to check from which method the electrons will be emitted. So here what we do, we calculate the frequency of the light used using the wavelength, which is given c over lambda. So 3 times 10 exponent 8 or power 8 divided by 546 times 10 to the power minus 9. So we get 5.5 times 10 to the power 14 hertz. This value, if we compare it with the given threshold frequencies, we see that the 5.5 is greater than 5.2 and greater than 5.4, but it's less than 5.6 and 5.9, which means, let me concentrate here, which means that the frequency of the used light is greater than the threshold frequency of both metals A and B. Because to have photoelectric emission, the frequency of the light should be greater or equal. And here it's less than C and B, so it doesn't work. So this light can remove electron only from metal A and B. So therefore, the photoelectrons will be emitted only from metals, from the surface of metals A and B. Okay, so we were starting with this question before, so for more explanation you can go back to the previous part. Okay, now we continue with question number 3. Question number 4, I mean. Here, this question is very important because it covers many ideas. Okay, let me start together. It's question number 4. The work function of energy of a certain method is given. So here, as we see, the work function is given. It's giving me the work function. It's given in joule. And asking me to calculate the longest wavelength. Calculate what? The longest wavelength for which photoelectron is emitted. Which means, when we say longest wavelength, we are looking for lambda maximum. Okay, what we said before, what do we mean by lambda maximum to have photoelectric emission? It means he's looking for the threshold wavelength. It's very important, because that, when we explained in the previous period part, I was concentrating on this point. Every time they ask me to find the maximum wavelength required to have photoelectric emission, that means he's looking for the threshold, the threshold wavelength. And at the same time, we have the work function, so it's very easy to get it. So what I do, part 1, I write the work function. It's equal to hc divided by lambda threshold. So implies that make lambda threshold subject by replacing phi with lambda, replace. So lambda threshold will be equal to hc over the work function. Of course, to get the answer in meter, you should use joule here. And it's okay, it's given in joule. So it should be equal 6.63 times 10 exponent minus 34 times 3 times 10 to the power 8 divided by 4 times 10 minus 19. So the answer of the wavelength here will be 4.97 times 10 exponent minus 7 meter, or 497 nanometer. It's the same. So this is the threshold wavelength, the maximum or the longest wavelength that can remove electron. And if I use any wavelength greater than this value, no photoelectric emission. Now part 2. This metal is irradiated with ultraviolet radiation with wavelength 250. 250 is less than, that means we have photoelectric emission. Ultraviolet is high energy radiation. Means we are working with a wavelength less than the visible light. Calculate for the emitted photon, emitted electron, the maximum kinetic energy. Here, of course, I need to, because the wavelength is given, the work function is given, so I can get easily the kinetic energy using Einstein's equation. Kinetic energy maximum, this is part A, equal to E photon again. So as you see, always I start with the main formula minus the work function. The E photon I don't have, but he gave me the wavelength of this photon, so I can replace it with hc over lambda, and the work function already given, 4 times 10 exponent minus 19 joule. Don't forget, here we have a joule, and this gives me joule, so the answer will be normally in joule. Okay. So I substitute. Just a minute. So 6.63 times 10 minus 34 times 3 times 10 to the power 8 divided by the wavelength, which is the wavelength of the used light. It was 250 nanometer, means times 10 to the power minus 9 minus 4 times 10 exponent minus 19 joule. So here we have a joule and here we have a joule. So the answer will be in a joule. The answer will be in a joule. Okay. So the final answer will be 3.95 times 10 minus 19 joule. Okay. Now the last part was to calculate the maximum momentum. The maximum momentum for this electron, for the emitted photoelectron. Okay. We need momentum. Just to remind you, this is part B. So in part B, we need the maximum momentum. Momentum, as you remember from last year, it's mass times velocity. Or mass, we can use here speed as a scalar. It's actually velocity, but we don't care too much by the direction here. We need the magnitude of this momentum. So the mass of electron, because the photoelectron is moving, and the maximum speed of the electron. So to find this momentum, you need to find the speed. So without the speed, the mass is constant. It's always given. It's like 9.11 times 10 exponent minus 27 kg. This is the mass of electron. It should be given. And the speed, the maximum speed, I don't have it, but I can get it from the kinetic energy I found. You see? So to find the maximum momentum, we need initially to calculate the maximum speed. So first step, I use the obtained kinetic energy. Kinetic energy maximum is equal to half mv square. So V will be equal to kinetic energy divided by mass of electrons square root. Okay, so we do this calculation on calculator, and we get the answer of the maximum kinetic energy, 2 times 3.9. So we get here after, so if we substitute 2 times 3.95 times 10 exponent or power minus 9 divided by 9.11 times 10 to the power minus 27. So the speed, or the maximum speed, will be, after using calculator, 9312.2 meter per second. So this is the speed of electron. Now, as a second step, after getting the speed, it's very easy to know momentum. So momentum equal mass times V. The mass of electron is 9.11 times 10 to the power minus 27 times the speed we get, it's 9312.2. So the final answer will be, should be, we have answer here, like 8.48 times 10 to the power minus 25. So 8.48 times 10 to the power minus 25 kilogram meter per second. Why kilogram meter per second? Kilogram because we have mass, meter per second because we have speed. So this is the maximum momentum of the emitted photoelectron. So the last question in this part will be on question. It will be question 5. Let we read together, write the given together to solve it. This is higher level. Okay, this question is higher level. It's like look like reasoning question. Let we do it together. A light source with wavelength lambda illuminates. That means another calibrator. Okay, illuminates a metal and ejects photoelectrons with the maximum kinetic energy. So initially, we have light with wavelength lambda, and this light leads to photoelectric emission, and the kinetic energy maximum is 1 electron volt. So when I use 1 lambda or this lambda, it gives me kinetic energy 1 electron volt. Okay, so this is lambda 1. We can call it lambda 1. Okay, we can call it lambda 1 if you want. So here, lambda 1 is equal to lambda, and this is kinetic energy 1, because I'll change it. A second light, so another light with wavelength lambda over 2. So I have another lambda, lambda over 2. Lambda 2 is equal lambda over 2, means half the previous lambda. But it leads to kinetic energy, maximum kinetic energy 2 will be equal to 4 electron volt. So because if I don't understand the given like this, it's very hard to get the answer or to find it. So asking for the work function of the used metal. So I use it same metal. This is very important. Same metal means same work function. So we're changing the light, the kinetic energy is changing. You see? But the metal is not changing, the work function is not changing. So how to get the answer? Initially, I think normally I use Einstein's equation using the first given. So Hc over lambda, which is E photon, equal to the work function plus the kinetic energy 1, which is 1 electron volt. You see? To find work function, we don't have the wavelength, so it doesn't work. Okay? So at that time, I realized that I need to try it with the second equation. Because I see here, I have 2 unknowns, which are the wavelength, because H is constant given, C is given. So to find the work function, you can't because you have two unknowns. So it doesn't work. So at that time, I realized that I need to try another equation. So if I try another equation to write HC over lambda, HC, this was HC over lambda 1, right? And this lambda 1, it is equal to lambda. Now I have lambda 2. And this lambda 2 is equal to lambda over 2. You see? Equal to the same work function plus 4 electron volt. Is it clear? So here we had lambda 1, here we have lambda 2. Same issue, I have two unknowns. So little bit, let me think more a little bit. So let me simplify more these two formulas to make them easier for imagination. So I have like two equations, HC over lambda again, equal to the work function plus 1 electron volt. And if we put lambda over 2 here, 2 goes up, so it gives me 2HC over lambda equal work function plus 4 electron volt. See? So our aim is to find the work function. So we need to keep it because I need it. But I need to get rid of lambda. If you concentrate well in these two equations, see the two equations, how to get rid of this and having only the work function. Simply what I do, I can use the value of HC over lambda here, which is phi plus 1, and I substitute it in the second equation. And instead of HC over lambda, which means instead of HC over lambda in the second equation, what I can put phi plus 1. So I will get one unknown. So what I do now, substitute equation 1 in equation 2. So this is math. So instead, so we have down 2, and instead of HC over 2, what I write? Between a bracket, phi plus 1 electron volt. On the other side, what I have? Phi plus 4 electron volt. You see, I have only one unknown now, which is required, the phi. I expand 2 work function plus 2 electron volt equal to the work function plus 4 electron volt. So the working, it becomes very easy now. So I isolate, or I keep the phi's on one side. So now 2 phi minus 1 phi equal 4 minus 2 electron volt. So 1 phi is equal, or the work function will be equal to electron volt. So the work function is what? 2 electron volt. This is what was required. Okay. If I need now the wavelength, I can substitute it in one of the equation and get the wavelength, but it's not required. Okay. Thank you very much. Thank you very much. Salam alaikum.